Hello, everyone, and welcome back to Code with Italians for our last stream before the summer break. And
Yeah.
because the summer is getting here and devices get hot in the summer, they needed performance. I don't know. This is the weirdest introduction I've ever
Really?
done.
Really? Wow.
You're welcome.
What are
You're
you?
welcome.
Wow, that was so smooth. Super smooth. Super smooth. Jesus Christ. Okay. Anyway, Rahul, thank you for being here.
Sorry, Rahul.
But I'm gonna be the adult of the situation here. So welcome back for another episode where you bear with us for about 90 minutes. So how are you doing, by the way?
Good. Yeah, I don't know how I was doing fine before that joke, but now I'm like, I don't know.
Oh, sorry.
Nice.
I'll try not to make more jokes.
Yeah.
So
No.
what are we doing today?
Today we'll do something very different. Today it's not going to be the usual, let's just look into Perfetto or our method. We're looking at method traces, but sort of tangentially. It's just we just happened to look at method traces because I think my goal with this talk is to try and make you more comfortable with looking at bytecode, and trying to understand what is going on, and then maybe even going a step further and saying, oh, what if I just tweak bytecode while keeping some intrinsics, and then I get a deeper insight into what my code is doing, and even what third-party code might be doing under the hood when I call an API, and so that's the kind of goal that we have for today. So we'll start simple. We'll look at a very simple Java application. We'll start looking at some very simple bytecode in the beginning, and then we'll go dive deep into a custom Gradle plugin and an Android application, and that's when we'll connect all the dots.
I hear a big brace yourselves
coming
up.
So that's. I don't know how useful this is. It might be useful if you're the performance-oriented person and you aren't trying to understand, what does this actually mean? What is going on in this bytecode, and is this good or bad? And so this mainly started because I wanted to be more comfortable reading bytecode, and I was I have to force myself to do this, and
it can
to better
be a
understand.
pain.
Yes. Although the tools are super nice these days. I wonder how people did it back in the day when then the tools didn't exist, but now it's a lot nicer.
I mean, I still have to deal with Smiley from time to time, which is interesting.
Yeah. Today, thankfully, we'll just be looking at the JVM spec. We will not look at Smiley or Buck Smiley or any of the variants. We'll be doing things by the book. So as few hacks as possible for the most part, I promise. So yeah.
But then we'll have at some point to do and to go and look at Smiley. So for those who don't know, Smiley is the decompiled language that Dalvik bytecode gets translated to when you use something like APK tool to take an APK and decompile it. So if you're doing reverse engineering, you have to deal with that a lot.
Yeah. Yeah. So whenever you're ready, we can start the live share.
Mm-hmm.
Do you need to do the even thing?
Yes, very quickly, because I want to see things on the nerd side. Thank you for being with us. Thank you for joining us live and on YouTube. If you want to support us for free, you can join your Amazon Prime account with your Twitch account, and then you will be able to see the toggle that allows you to subscribe to a channel every month for free. This will support us paying the bills for websites and printing stickers and giving away things every now and then, and especially at conferences. We also have a discounts code for that conference in Berlin and in London and in Italy. So if you plan to go and to buy a ticket, reach out, please. Maybe we can help you with some discount code. And yeah, if you want to buy our merch or become a subscriber, check the link in the description. You can join our coffee subscription, or you can buy things from our store. Thank you.
I just put in the chat the link for the 25% off for
Fantastic.
Droidcon Berlin. So if anyone just realized that Droidcon Berlin is next week and they want to go and they want to pay a bit less, then use the code. We'll probably going to be sharing the one for London at the end of the stream, maybe.
Sure. I mean, you tell me.
Decided.
Yeah, I mean, London is pretty in the future, right?
Yeah,
Is it
it's
October?
31st of October, 1st of November, I think.
Yeah, so you can plan ahead, and
Yes.
yeah, end of November you have Italy then, so that's good. Let's go.
Okay. Rahul, you ready? Shall I share your screen?
Yes, go ahead. Go for it.
Okay. You're on. You
Alright.
probably want to zoom in a bit because it's very tiny text.
Hold on 1 second. I have a new keyboard, so you know my shortcut game is not as good as it should be. Is this better?
Yeah, it's probably fine.
Right. Maybe
I'm
this...
sure someone will tell us in the chat.
All right. Okay. Cool. Yeah. So yeah, so we'll be looking at the virtual machine instruction set later. Like, don't worry about this. It's just happened to be the first window. So yeah, let's go at the
Easy start.
Easy start. Yeah. All right. So I think what we'll start off with is basically get familiar a little bit with bytecode, and then just see what tools are out there, so you can sort of make sense of what's going on. And right now, if you notice, I have two modules here. I have a if you look at my settings.gradle.kts, I have a project called ASM and I have a project called example. And this is just a simple playground setup, so you can sort of like play around with messing around with bytecode, and you can see the results very quickly. And this like makes for a nice little way to experiment with the transformations that you want to make. So before we make any transformations, let's just like figure out let's just see what we have in the beginning. So in my source main Kotlin, I have I have this code. I have a very simple program, which is which has a single. We have an entry point main calls method one. Method one calls method two. I pass in a bunch of arguments. It's like they're sort of irrelevant, to be honest. I'm just trying to make you see a little bit of control flow. And then method two calls method three, and then I just have print lines. And like if I were to build this, if I just build project and Gradle daemon spins up correctly. Once all the code gets compiled, you will see a list of class files here in the build folder. So if you go to the build classes folder and you go to main, com, Rahul, you see these classes, right? Actually, let's just delete this for now. And then we can see. Yeah, so like this is the entry point. So if you did not have any other additional IntelliJ tooling installed in the IDE and you click program kt.class, this is literally what the compiled code looks like from when you just look at the default tooling. So you can see that there's an entry point main, method one, method two, method three, they all return unit, right? So this looks familiar, but this is not the full story. So if you have a plugin called Byte Code, if you have this plugin, let me just call out the name of the plugin so you know which one to download. There's a few, but the cool one that you want is the it's called Byte Code Viewer. It's called Byte Code Analyzers by Marcel Klimenel. Yeah, so this is a fantastic tool. I found this to be like extremely useful to get, because it gives you like many views of the same bytecode, and then it tells you exactly what's going on. So what we'll do is we'll just like drag the class file into this part of the IDE, and then it'll just now show the program structure. So you can see that this class is compiled for JDK using JDK 17. It has a bunch of debug information. The name of the source file is called program.kt. Has a bunch of Kotlin metadata, a bunch of annotations and methods. Let's just go to the plain view. So this is the actual bytecode. Like if things are slow, don't worry about it. Like sorry, if things are small, don't worry about it too much, because it's not very important to look at this stuff yet. But you can see. I wonder if I can make this a little bigger. Hold on. Well, I don't know if this actually respects the zoomed in view. Maybe
it doesn't look
maybe I'll
like
just,
it.
It doesn't look like it. Let me just copy this out so I can just like paste it into an editor.
We
and then
found the bug.
Yeah, didn't take too long.
And I didn't break it.
All right, let's open a new window and let's just drag it to this part of the screen. And let me just change the size of the decorator. I think the default size, I think it's set to, I always forget what the font.
I think there's a font section.
Yeah, I'll just set it to like, I don't know, 28 or something.
Yeah,
maybe.
whatever.
This is better? Okay, better. Okay.
Yeah.
So yeah, so you know, here we are just looking at some bytecode. And you can see that we have a class com Rahul Rav program KT. And then this was compiled. So like, you know, there's some debugging information. And we have this method one. And there's a bunch of, you know, there's a bunch of stuff going on here. And then you have, you know, you can see method one calls method two somehow, like, you know, you can sort of like discern what's going on. And then there's a bunch of metadata here about max stack, max locals, and a bunch of other things, right? Like this is what the shape of the bytecode typically looks like. So now this is not super readable yet. So let's go back to the IDE and let's click on the decompile view. Now this is the decompiled view. If someone took the class file and then they basically ran it through a decompiler, this is what you would see. And the decompiler looks something like this, where let me just go back to the IDE. We just paste it in here. So now you can see that there's a bunch of Kotlin metadata here, which is expected because the Kotlin compiler basically adds a bunch of metadata to your class. And then we have method one calls method two, you know, all the print lines from the Kotlin standard library have been replaced with system out println. And then you have var 0 and a string, and then basically it looks exactly like the code that we wrote. And so the mapping it makes a lot more sense here. So yeah, so that is good. Now there's something called the constant pool. A constant pool is a list of all the strings that you have defined in your class. So if you notice, I have method one, I have inside method one, I have, you know, these are all a bunch of other things, but like you have the constants that you have also defined. Like here I have a UTF-8 string called Rahul Rav, which I basically pass as an argument. So there's a bunch of constant pools. There's a bunch of constants in the constant pool as well. All right. Now that you know what this typically looks like, now we can start doing some cool, clever things. So let's actually like do a quick bytecode sort of like let's just go back to this view of the bytecode, the original bytecode, the raw bytecode, and let's try and make some sense of this. So if you see method one, it's public static final method one. The V here just means it returns void. So the JVM spec says anything that follows braces is the return value. So here you can see that the method returns void. And this is a bunch of like debugging information for the debugger. So when it says line number 4, you know, it just means that this was line 4 in the source program. So when the debugger is sort of like doing a step-by-step debugging, it knows which part of the bytecode maps to which part of the source code. So you can sort of like be comfortable with your view while the virtual machine knows how to like jump to the next going on. And there's something called LDC. And you can see it's a string that we've defined called inside method one, right? This came from our program where I basically call inside method one. So there's an LDC, and you might be wondering what like an LDC is. So an LDC is essentially let's coming to the interesting part. Let's actually looking at the Java machine instruction set. For those who don't know already, the JVM is a stack-based virtual machine. So it literally pushes and pops operands on top of a stack, and it just executes your program. And so let's actually, if you look at the instruction, like, and the stack-based virtual machine defines a list of opcodes, and these are like basically agreed upon instruction sets that have a you know, a predefined meaning, and like the VM knows exactly what to do. So in this case, we're looking for LDC, and then it basically says push item from the runtime constant pool, right? So basically saying we're pushing an item from the runtime constant pool onto the stack. So if you go back here, if you had a stack marker here, so our stack here would have actually. So at this point, our stack would have a string from the constant pool called inside method one, right? That would be on top of the stack. Now the second instruction that's being executed is called get static, and you can see it's calling Java lang system.out, and so it's clear that it's calling system.out. The out is a static field on system.out, which is actually of type print stream, right? The L prefix just means it's a class. Anytime you see L, it means it's a class, and the all classes are package prefixed with a slash. So this literally means there's a class called java.io.printstream. So that's how you read it. And so here you're saying get the static field system.out, which is of type printstream, right? And now what happens is we have system.out, which is a print stream on top of the stack. The bottommost part of the stack was the constant method inside method one, and on top of that was the print stream that we did, but that we added to the stack. Now we have an instruction called swap, which just swaps the order of items in the stack of the last two items, right? So it basically moves the constant to the bottom. It moves the constant to the top, and then moves the the print stream to the bottom. So before here, in our stack, we had something like the system.out was on the stack and then we had and then we had in our stack we had the constant, right? Where the items on the right are basically the items on the lower in the stack. But here, after the swap operation, what we did is we made the constant be on top of the stack, and then we basically moved system.out to the bottom. So now the order of the items in the stack has been reversed of the last two. Now we are calling invoke virtual. Invoke virtual is basically means anytime you see invoke anything, it means it's invoking a method, right? And you can see that it's calling printstream.println. So we are calling system.out.println. So you can see the receiver is of type printstream. The method is called println. It takes a Java lang object. The println takes an object. It can take a string. It can take an integer, anything, right? So like this is the input type to the argument. And the output of this method call is a void. So basically, it doesn't do anything else after. It's just an invocation of the method. So the calling convention of the virtual machine is that so now what happens is because it knows there's an argument, the argument is always like the one on top. So essentially what's happening is it's basically popping as many things as it needs. It looks at the number of arguments, and it looks at the receiver, and it pops as many things from the stack as it needs. And the calling convention is that the item that's the receiver is on the lower, is basically lower in the stack and not on top. And so essentially what we're calling system.out.println, passing it the constant as the argument to the function. And at the end of this method, after the dispatch of this method, there's nothing on the stack.
I have a question.
Yes.
So if you have multiple parameters,
yes.
Are they on the stack in reverse order? So the first parameter is at the bottom and the last is at the top?
That's right. Yeah.
Okay.
So the further right that you are, the further on top that you are, I think. I may be wrong here, but we can easily prove that with another example.
Okay. Yeah.
But that's the idea. So the idea is that you have items on the stack and you have the receiver on the bottom, and the calling convention is that the receiver is on the bottom. And then when you execute a method, that's what's happening. It's just like manipulating the stack, executing the method. If this were to return an integer, right? Let's just assume that if this were to return an integer, it would take that integer and push it back onto the top of the stack. So you can consider doing something with that integer. If you were doing something like that, that's what would happen. But in this case, because it's returning a void, I deleted it by accident. Yeah, because it was returning a void here. It doesn't really do anything here. So essentially, what you're doing is you can now it makes more sense, right? So now when you see LDC Rahul, it just means it's loading a string Rahul from the constant pool, and then it's calling program kt.method2, passing in the string and getting a void. The J here means that the integer is the first argument. I think J stands for hold on. And if you notice like these if you see this, and it strikes, like if you see, like if you think like you've seen something like this before, you have, right? Like if you go to if you go here, and let me zoom in a little bit.
It's our friends, the baseline profiles.
Yeah.
If you
tell me that you worked on this stuff without telling me that. I mean, he just typed the URL. I mean, who does that? Nobody does that. Everybody just search it and then they click the first link.
If you yeah.
We need to get paid. 2 searches.
Yeah, those are the one that contains the ads. Come on, nobody.
So if you notice these types, right? Like this is the same thing that you've been seeing. Here, J just means it's a long. The long is the first argument, right? And you know that it's true because our method 2 basically took a long as the first argument, and then the second argument was Java lang string, right? Like those were the 2 arguments that the method took. And so here you can see, and because we're not actually using these methods, let's actually do one thing. Let's actually rebuild this by actually using these arguments, and then we can we can maybe take advantage of that. So let's say, how do we do this? Like let's say let's just say val alias long equal to long. If you're wondering what I'm doing, I know it'll make a lot more sense once I'm done writing the code.
That's gonna be a lot of bytecode. That string interpolation.
I'm just aliasing it, so I'm also like adding local variables, so you can see what that does and what that looks like in the bytecode, right? And then I can see, right? So basically, I'm calling these, and like ignore these warnings. Let's just like build this again. So now that we have this and we have some new code, let's actually like load it up. So if you go back here, drag this back, look at the plain view, you can see method 2 is doing something more. Yes, let's actually copy
just
the whole
a few
thing again.
more things.
Just a few more things. So let's actually, oops, sorry. I keep doing that. So let's just like update our view of the world. And then now let's go look at method 2. If you notice, we have some new parameters here. So load and store literally means load the constant, load a long constant to index 0. So basically, there's we also apart from we're basically loading some constants to the stack because there's a long constant and a string constant, and then long constants are special. Basically, all the primitives have their own special instructions, and all references have their own instructions. So load just means it's a long load, and load just means that's a reference load. You're loading a reference to the stack, right?
So that's a pointer essentially.
The pointer essentially, and like this is basically calling make concat with strings, and you can see that it sends it a long and a string, and then it returns a string, and then you can see that there's like a whole bunch of stuff happening because it's using string concat factory. But at the end of the day, you can see that it's basically the arguments here are the string inside method to something, and then like there's a placeholder here, and then there's a whole bunch of stuff here. Like it's super hard to read because string concat factory does a lot of things. There's a lot of things to make things performant. But if you notice, it's basically it has it's basically getting the static reference to system.out, and at the end of the day, it's calling. Now this is basically calling invoke dynamic. Invoke dynamic is a special instruction that invokes a lambda. Basically, like string concat factory is being invoked with a lambda. So there's a method handle that's being passed to the lambda. It gets an output string. So the output is a string, so that gets loaded onto the stack. And then we have a static system out print stream that gets loaded onto the stack. Then we swap like we did before. And then now the calling convention holds, and then we just call system.out.
So
does that make sense?
I think we need to do like one step back, which is there's invoke virtual, invoke static, and invoke dynamic, which
Yes.
are three different ways of invoking three different things, right?
Right.
So invoke
right.
static invokes a static method.
Static class method, yeah.
Invoke virtual invokes a non-static method on an
That's right.
instance, for example.
Mhm.
And then invoke dynamic, as you said, is used for dynamic stuff like lambdas.
Yes.
Okay. And what is happening here is I'll go through the code, the byte code as I see it, just to see if I understand it. So L0 loads the long in 0 and then stores something in 3.
Yeah.
L1 it loads the string into the first string. No, the only string actually into 2, and then stores it.
By the
into
way,
5.
L store and A store just store these things onto the stack at those respective indexes.
Okay.
Right, and
so
then
load
you're
0
doing
is
L
loading
load
into a somewhere into a memory the string or the number, and then putting
Yes.
it on the stack at position 3.
That's
And
right.
A load 2 is loading the string from the constant index 2, I guess.
Right. Yes.
And it's storing it on the stack at position 5.
Right.
Then it's loading from 3 and loading from 5. So that means
Yep.
putting those two things on the stack,
Yep.
right?
Yes.
And then it's doing the string concatenation, which I'm not even going to try and parse. We
Yeah.
just know how it looks in Kotlin. That's understandable.
I mean, you can tell that the arguments that are being passed are an integer. Sorry, a long here. If J stands for a long,
then a class.
and then
the
a
string,
class, right?
Yeah. And it
and then it
returns
returns
a
the
string.
string. And so at the end of this invoke dynamic, the only thing that you have is you have all the previous things popped from the stack because they've been used as arguments to the method call. And the only thing that's left on top of the stack is the return of the method call, which is invoke dynamic.
Yeah.
Right.
So after running this, you have the interpolated string as the only thing on the stack. Then we do the same thing we were doing earlier. So we get the value of system.out and we put it on the stack. Then again, we swap it because we want the parameter first and then the receiver. And then we invoke the print line method on the receiver.
Yep. Okay. That's right. Yeah. So yeah, now you know almost everything there is to know about Java, reading Java bytecode, which is pretty neat, right? There are some like fancier instructions. For the most part, it's not as intimidating as you thought, or at least like for me, it was like a huge revelation saying, oh, actually, this is not that bad. Like once you understand how the stack is being manipulated and what's going on, it's actually a lot simpler than I expected it to be, which is super nice.
It's just very verbose, I guess.
It's just super verbose. You never want to do anything like this manually. Like you wouldn't want to write this manually, right? Like you thank God for the compiler where it's like generating all the stuff for you. But like it's useful to know just by looking at bytecode what is going on, and I think you get an idea about like how expensive things might be, right?
Yeah.
Because if there's like a ridiculous amount of bytecode and like your simple method call changes into like 100 lines of like invoke dynamic, then you know something strange is going on. At least you have an inkling that wait a minute, like is this doing
there's
like
some
something
magic
not
here?
There's some magic here that I should probably like delve deeper into, right?
We have a good question on the chat from Mark, which is why? So if we end up always swapping, why don't we just load things in the right order directly?
You could do that too. It's just like how the code was written, right? Like I honestly don't know why the compiler does this. So I think to the compiler's credit, the compiler is trying to do things do as few transformations as possible while still making debugging easy. And it basically leaves it to the hotspot VM to sort of optimize this bytecode and then do all the things. So I think like once the VM is actually picking up this bytecode, this is not how it's actually executing. It just scans the bytecode and says, oh, I'm doing the swap, so I should just like reverse the order and then just execute it out of order. Like if it's a simple load and store, there's no side effect to that, right? So unless there's an invoke dynamic or an invoke static that may have side effects, it knows exactly what might be going on in that case.
It gets just in time compiled from this bytecode to the actual native
instruction. Yeah. So even this is not the full story. That's why this is like closer to what is running actually on the computer, or actually I should say on the virtual machine, but it's still not the full picture. But you get like
optimized yet.
Yes, it's not fully optimized yet, and you don't want to guess the kinds of optimizations that the actual virtual machine is doing, because those things change all the time, and sometimes. And that's why you want to use things like Compiler Explorer, the tool the really cool tool that Roman wrote, to see what art would actually generate, like with final art assembly. Because I was talking to Roman the other day, and he's like, yeah, looking at bytecode is like not good enough. You have to go one level deeper, and then you have to actually look at what R8 is doing and what the assembly is doing, like what the actual assembly that art produces at the end is, to know exactly what the characteristics of the code that you wrote are. And like, I don't think most people need to dive in at that level, but like it's really good to know that you have those tools available for you if you want to look at them.
Yeah.
I mean, how Roman is it? The bytecode is not enough. You need to go deeper.
Yeah. But then arguably, like
it doesn't get more Roman GUI than that.
Yeah. You learn a lot about how your program works when you look at the assembly. I mean, I think looking at assembly is also like a similar experience. Once you know how to read it, it makes complete sense. But like, I think the getting to know part is the hard part, right? Like, I think once someone explains it to you with some tools saying, actually, it's not that bad, just have these few rules in your mind, and it's just like, this is how the program is being executed by the CPU. Things make a lot of sense, but yeah. But these are all the costs of this. These are all the abstractions that we built, right? Like there's the actual assembly. There's a VM in between that's doing garbage collection for you additionally, and then there's the compiler that's generating bytecode. And the thing that you're writing is actually Kotlin, which is like so many levels of abstraction away. And sometimes it's super useful to think about like how the code gets transformed, especially if you're doing something super frequent, and you want to make the cost of it like as cheap as possible. And so you want to go do all the clever things that compilers typically wouldn't think of, because they know less about your code. They're just doing general transformations. Does that sound? So like, if you think we have a good enough handle on what bytecode looks like, then we can look at the next step on like what we should do to sort of make some transformation on the fly. Sound good?
Yes.
Okay, so I will proceed assuming you've bared with us so far, and
it's probably fine.
Sure. I mean, there's gonna be a recording, so that's my only hope.
Yeah, so you can play it back again and again and again.
Yeah, but 0.5x. So it's gonna be
let me undo all the changes that I had here, because they're like I don't like squiggly lines in the IDE. And then so now like, let's assume that we want to like actually measure the cost of these methods, right? Like a naive way to do this would just be basically like, inside every entry and exit, I would basically do like, val start at equal to system.nanotime, right? And then I'd basically say val time taken equal system.nanotime minus start at, right? And then I would just like basically log something. Oh shoot, my keyboard. Sorry.
That's what you get for getting a new keyboard.
By the way, what keyboard is that? Because I'm looking for something like my Logitech with the very thin keys, but with a wired with a cable.
Can you see the keyboard? It's like super weird.
Is it like a split keyboard or sort?
It's a split keyboard, but the key layout is very different from like a conventional key layout. Let me try.
It's like a Dvorak.
It's not a Dvorak. No. I don't hate myself. No. Let me
Not
show
that
you what it
much.
is. Not that much,
Yeah,
at
man.
least. Actually, wait a second. Let me show you. It's made by a company in the Bay Area called Keyboard.io, and they have this like super ergonomic keyboard, which I thought I should use because
Breeze. You're fancy. That's what you're saying.
No, I thought I should use this just to give my hands a break and like actually like learn how to type properly. And so
Yeah.
it's been an experience getting to use this keyboard because the layout is so different. And so yeah, that's why I struggle. Anyway, going back to the code, we have a start marker, we have an end marker, and we basically want to say, method one took like these many nanoseconds, right? And this is not the full picture. You also want to actually like instrument like every single method that is being invoked, so like time before and after like this method call. So you get like a recursive view of like every single method dispatch that's happening. And like in theory, this is what you want to do, right? What you want to do is essentially instrument every single method entry and exit. And you want to build a timeline view of like what happened first, who called which method, and then how long did that take, what thread was that on, and stuff like that. So this is what you want to do. But like writing code that actually looks like this is super cumbersome. You don't want to write code like this, right? Like if someone sent you a code review with this code, you'd be like, what the hell's going on here? Like why is there so much instrumentation all the time that's happening, right? So you don't want that. You want to be clever. So you want to do something better, which is essentially you want to add bytecode that adds these method entry and exit points to your program dynamically at build time. Like, so when you're looking at the code, it looks normal, but when you actually build it, it looks something slightly different. Like it actually has the method entry and exit built in. That's sort of that's kind of what Art is doing under the hood when you turn on method tracing, except it's doing this at the assembly level. So it's actually instrumenting every single method entry and exit at like the Art level, at the virtual machine level. But we'll do this at the bytecode level for the few defined entry points that we know about, right? Like the only few entry points that we care about. And then that makes it a lot simpler, and that makes the trace a lot more terse, because you don't end up looking at traces that show you the detailed implementation of like Java lang string.concat, for example. Like you don't want to know what it's doing. You only care what your program is doing. So in my case, I only care about what program.kt is actually doing and like what it looks like. Okay, with that context, let's look at let's look at, this is the class file. Actually, I should not look at this anymore. Let's actually look at another file that I've defined. So I have an interface tracing here, and you might like, so basically what we want to do, like I said, is we want to instrument every single method entry and exit with a tracing.begin section, the corresponding name, and a tracing.end section. And our tracing implementation is essentially going to record the name of the method, and it's going to keep track of like all the information that we want, like how long it took, what was the caller, and potentially, because we know all the previous callers, on this thread that called begin section, right? And so we can sort of build that timeline view if you want. And we have this method where the implementation, I haven't really bothered to implement it yet, but there's a static field, there's a static method called getInstance, which returns an instance of this tracing interface. And all you can do is call begin and end section here, and that's it, right? Now, what we really need is, like I said, we want to instrument every single method call, and we want to only instrument classes that we care about. So ideally only in the package com Rahul Rab, because like we don't care about the things that that are our implementation detail. I don't care about the println. I don't care about what's happening, how long println takes, because I know that's something I can't control. It's coming from the Kotlin standard library, and for the most part the costs are fixed. But I can control the code that I write and what method 3 is doing. So I am only interested in looking at code that I control. So for that, what we'll do is now we'll try writing some ASM to manipulate the generated class file to sort of instrument the code to introduce these method entry and exit points. Does that make sense?
Yep.
All right, so now let's dive into some ASM. So if I look at the build Gradle KTS, you basically have to define ASM core. ASM util is an implementation dependency, and there's a bunch of test dependencies as well. But the class is actually very, very straightforward. Like it looks like a lot, but like I'll break it down slowly. So ASM uses a class visitor, like it uses a visitor pattern. So what it's giving you is basically it's giving you a class visitor and a method visitor. Like every single time it sees a method dispatch, it gives you like, it tells you that it's visiting this method. And then you can choose to do something that's beyond the default implementation of what ASM's doing, right? So here I have a tracing class visitor, I just call it. And here I'm just assuming that I'm using the ASM9 opcode set. It just means that I'm using a modern version of the bytecode. Like basically bytecode is also versioned because as Java evolved, they kept adding opcodes. So I'm assuming that the class files that I get are compiled are basically JDK 8 plus compliant. So I'm not like just trying to support things that are older than JDK 8. And I extend this class visitor. And essentially, I'm delegating it to the inner class visitor because it's the inner pattern. You're always given an implementation of a class visitor from ASM, which does the actual visiting. But then you can do something different if on a few conditions. So anytime visit method is called, I'm essentially calling the super.visit method, which is the implementation of visit method from ASM. It gives me a method visitor, and I create my own method visitor by delegating it to the underlying method visitor that ASM gave me. So I can sort of like tweak things.
You're decorating everything that
exactly. So I'm decorating.
Exactly.
Yeah. Okay. And now let's look at what the tracing method visitor does. It basically has the method visitor, the API. I'm extending the method visitor type. And every time you get a method visit method instruction, which is what this means, it gives you the opcode. It gives you the owner. The owner is the fully qualified owner. So in this case, it would be Java/lang/string.
Okay.
For example, if we were calling a method on string, the name of the method, which is the name, like this would be like something like println. And this would be the descriptor of the return type. So this would be all the arguments that the method takes. So like remember the brackets J and L Java lang string, and then the return type would be plus the return type. So if you return void, it would have a V at the end, for example. So that's why. And then it'll tell you if this is an interface or not. If the method call is actually an invoke static versus invoke virtual, because if you're making a non-static call, this should be set to false, for example. Now. I mean, I don't want to annotate, like I don't want to decorate methods whose implementation I don't control. So I'm basically saying if it's in the Java package, if it's the Java standard library, or if it's the Android framework, or if it's Kotlin.foo or KotlinX.foo, I don't want to do anything. Like I just want to, that's basically framework code. I have zero control on it. I cannot control, I don't want to control it. So basically, if I want to skip instrumentation, I just delegate to super.visit method instruction and I move on. At that point, like that entire block of code is kind of like done. However, if I see some opcodes that I care about, so anytime, like remember, I want to intercept every single method and every single method call inside every single method entry and exit, right? So I'm basically saying anytime I see invoke static, virtual, interface, special, or dynamic, this is every single method call. I basically get the class name by doing a split on the owner because it's split by the slash, and I'm just getting the last bit of the. So if this was Java lang string, we would end up with the shortened name string, right? Because I basically ignore everything preceding the last token, and then I construct this trace section name, which is class name and method name. Remember, the name was the name of the method. So I basically now fully qualify the name. So I kind of understand better what the method name was. And essentially what I'm doing is I'm calling our tracing entry point. Remember, we defined this tracing instance, which was get static, right? Like it was a static field. It was a static method dispatch on the companion object for the interface tracing. What it's doing is basically saying, call com Rahul of tracing, get the static field called companion, and that the return type is tracing companion. And I have this backslash because anytime you use a $, which is the demarcating for an inner class, Kotlin thinks they're trying to do string interpolation, so I have to like back escape it, right? So all I did here is I loaded the tracing.companion static field to the top of the stack. Does that make sense? And then I'm calling invoke virtual, and I'm calling tracing companion get instance. And notice it takes no arguments, but it returns an instance of com Rahul.tracing. And because it's a virtual call, because it's not an interface, I'm just returning false because like there's only one implementation of the companion type. So I know that there's no other interface here. So here at the end of the day, after I call companion.getInstance, I'll have an instance of tracing on top of the stack, if that makes sense, right? And at this point, I'm calling LDC. So here I'm basically writing some custom. So all these things that I'm doing here, these are all custom methods that I'm now interjecting. I'm basically inserting myself into like what the bytecode visitor is doing, right? So now I'm calling LDC instruction. Remember, I'm loading the trace section name, the constant from that I have defined here. That is the fully qualified trace section name. I'm loading that to the stack, and now I have the name, and I have the actual instance of the tracing type on the bottom. So now the calling convention holds. So now I can just call tracing begin section, give it the input string that I basically have on top of the stack, and it returns void. So all I did was I created this trace section name, and I basically called begin section with that name. So far, so good. And then here I'm actually calling the actual method. So basically I'm delegating to the inner the visitor, and I'm saying do your thing, like actually fill out the details of what the method did. So I'm basically calling super.visit method instruction for the underlying for the method that we are actually decorating. And then I do the same thing again where I do the exact same steps, but here instead I call end section. So essentially what I did was for every single method entry point and for every single method dispatch inside that entry point, I'm decorating it with tracing.begin and tracing.end. Make sense?
Yep.
And if we don't recognize the opcodes, we just like no op, and we just do the normal thing that the visitor would do otherwise, which is it would just call visit method instruction. And so now that we have this decorator, so let's actually see how to use this decorator. So let's write a quick test to see if it actually works or not. Oh, actually, did I write this? Yeah, I think I wrote a test. Hold on. Where is it? Yeah, it's here. Okay. So I have a test program, oh yeah. So you might be wondering how I knew what the instructions were, right? Like to sort of like to know what the transformation I need to do is. Essentially, I wrote a test program which essentially has the code which I want to write, which I want the ASM visitor to write, right? Like this is the code that I want to see at the end. If you compile this, if I just build the project, and if you look at the build output, and if you look at the test program, it should be in test result, test classes, wait a minute, classes, test, yes, sorry. Okay. Yeah, test program.kt, let's actually go here, and let's just open up some bytecode, right? If you go here, and you look at the ASM view, it'll actually give you exactly what you need to do. So like, let me copy it from here into the editor so you can actually read it. Nope, not this one. And right now, if you see here, this was the ASM view of the bytecode of the class visitor that would have visited the code that I wrote. And you can see it's literally doing the same thing. So it's calling get static on tracing companion, and it's calling invoke virtual to get an instance of tracing, and it's calling visit LDC instruction main because the entry point of the program was main, and then is doing tracing begin section, and then it's doing tracing, it's calling the actual method one method, and then it's calling tracing.end section, right? If you look at this bit, that's exactly what that is doing. So this bit is just, it tells you exactly what to do. So I literally took this as reference and I wrote my decorator. So you don't have to guess what the instructions are. Like the Byte Code View does a really handy job in explaining what the ASM would have looked like. And I think you can use that as reference. That's how I wrote that code. So that's that. Let's go back now to our program. And let's just close everything here, and then let's go to tracing visitor test. This is the class file, and now it's time to put like everything together, right? So I have my program path, which is the program kt.class. So program kt is the class that we were trying to annotate, right? Like this is so if you go here, we have program kt, which comes from main. Hold on, which comes from the main source set. So this is program KT. This is the non-decorated code. So this just has the code that we would want to write. and we want the ASM rewriter to do the right thing once it sees the source program. So when you compile this class, it lives in source main class program kt.class. So this is the relative class path, right? So in my test, I'm basically saying, go to the classes of program kt.class. Just read the class inside the build directory. Just load the class file into memory, and then you use the ASM class reader. So this is a class reader class, and ASM can just read bytecode that corresponds to a class file into memory and create something called a class reader. And then you basically want to create a class writer. This is the output class. This is the one that you're transforming. So the class reader is the class that you're consuming. And then the class writer is emitting the transformed bytecode that you want to emit as a result. And you're basically saying you are basically, because you're manipulating stack information and local and potentially local and introducing new local variables, the bytecode spec actually needs to tally up like the number of items in the stack, the number of max items in the stack, and the number of locals at the end of every single method. Like it maintains that as a header. So you're telling ASM that you just recompute things after the transformation. So the bytecode lines up with all the transformations that I make. In case I add a local variable.
When it's creating the actual bytecode binary,
that's right.
It readjusts the numbers.
That's right. So that's what you're saying. You're saying recompute the maximum of the stack if necessary, and then recompute the stack frames if necessary. And then the tracing class visitor takes a class writer. Remember, the tracing class visitor is a decorator that takes a class visitor. Class writer happens to be an instance of a class visitor, so it knows how to write a class. And then class reader accepts a class visitor, and you're just skipping the debugging symbols because you don't want to do anything to the debugging symbols. You just don't care. Ideally, you would want to care about line number information if you want things to line up after the transformation. But in this case, you're basically saying for like simplicity, I'm just going to skip all debugging symbols, and I'm just taking the class reader and I'm basically piping the class writer through. So as I'm reading the reader, as the reader emits, as the reader visits every single class and every single method, it basically pipes through that information to the writer that can do the transformations necessary. Does that make sense?
Yeah, so accept starts the actual visiting.
Yes, this is the bit that does the actual visiting.
So class reader doesn't do anything until you call accept.
Exactly. And then once you finish the actual decoration, class writer has a handy 2-byte array, which gives you the byte array of the transform type. You take that output and you simply write it to a class called output.class, just for simplicity, so we can look at so we can inspect the bytecode after the transformation using the same tools to make sure that things work, right? So if I run this, it'll basically find the class program kt.class, and then it'll do the decoration. Now let's see, there should be a class called output.class. And let's see. So here you can see that there's a class called output.class, which didn't exist before, right? And I'll open it, and it has the exact same shape. Because that's what we are transforming. We are transforming program.kt, which had the same shape, but except we just instrumented a few methods, right?
Yeah, and so let's look at that inside of the methods.
That's right.
A few instructions.
So let's see what we ended up doing in more detail. So if I go back to the Byte Code Viewer, and I just drag this class file here, and I'll look at the decompiled view just for simplicity, and I'll copy it into the editor so we can see it, so we can look at it. So now you can see that method 1, I called begin section method 2 before the call to method 2, and I called end section on method 2. Right? So basically every single method entry and exit got instrumented correctly. So I have main instrumented method 1 before calling method 1. And then method 1 calls method 2, and before the method 2 was called to method 2 was dispatched, it basically inserted those trace sections. And then method 2 inserted trace sections before the call to method 3. So now you basically like did something very simple, but like the output is so transformational, right? Like you basically now know how to transform bytecode on the fly to do just manipulate it a little bit to get the shape of the type that you want.
Yeah.
And this is super powerful because you can do a lot more than this, right? This is a very simple example. But imagine.
Sorry. Could you? So what we're doing here is we're saying every time we see an invoke, then we add a start section, a begin section before, and then an end section afterwards.
That's right.
Would it be also? It's also possible to do it to inject those inside of the method being called itself. So when you see, oh, this is a method, I'll inject begin section here, and I'll inject end section just before the return point.
Yes, you can do that too. Like I mean, you would just have to tweak the decorator slightly differently, because every time you would do the visit method, you would just like insert the begin and end.
Yeah.
But it's basically doing the same thing. Here, the reason why I did things this way is that the entry point is what matters, and I'm basically I'm instrumenting what gets executed by the entry point.
Yeah.
As the entry point discovers more information, rather than like changing all the bytecode that may or may not be executed. So I'm starting from like a known point, and I'm slowly expanding my search to include classes that it reaches out to.
Yeah, and I guess if you have multiple exit points from a method, then you would have to instrument all of them with end
That's
section.
Right.
So this is just easier.
So this is just a lot easier.
Yeah,
that's right. So yeah, so like what we managed to do here is like we managed to instrument a method, and now we've built our own like method tracing engine, so to speak, right? Because tracing begin section and end section can record the thread ID, the process ID, the time. Like it can do all the things that you want it to do, and then just record that information in a trace. And at the end of the day, all you're doing is just like opening the trace in a viewer, so you can sort of make sense of all what's going on in your program.
Are we going to build our own Perfetto trace by the end of the stream?
Yes, we are. That's the goal. Right?
With better colors.
I don't think you choose the colors in the trace itself.
Right. This was the hardest part to explain. Now that you know the mechanics of like the actual manipulation, the rest of the stuff is actually super easy. All right, let's dive into that in more detail.
So what do we need to do still? We need to invoke our code automatically when building.
That's
so
right.
The stuff we're emulating in the test, we need to do it in Gradle, I guess.
That's right.
And then we need to write the implementation that writes the trace.
That's right.
Okay.
Makes sense?
Yeah.
All right, so let's go to our, so this was the Java playground. Now let's actually switch to our Android playground. So let me close this.
I see Ivan is mentally preparing to switch the playback speed to 0.25.
Yeah, at some point I'm gonna ask for the transcript, so I can put it on my Kindle.
You can use Gen AI.
Yeah. I'm gonna just sell it to myself as, oh yeah, let's experiment with the Gemini, that kind of stuff. So yeah, because it's a bit tough, especially when you say, oh, now it's easy, and I was like, is it though?
I mean, it wasn't written a Gradle plugin before.
Oh yeah, sure.
All right, so I have a sample app.
Yeah.
It does something very stupid. All it has is it's a Compose app, which there's a main activity, and there's a button which is centered on the screen, and basically it does nothing but it has a text field that says hello Asm, and I haven't even implemented what the on-click handler does yet. Okay, it's basically like a very simple vanilla app. And if you want to go to running devices, actually let me use my Pixel, and I'll just like deploy this. And this is actually a real device. Let me just like deploy the app so you know what it's doing. And okay, I should have built this app before. Now it's actually like doing all the things.
It's fine.
So yeah, it's like basically the app is not doing that much. It's literally a simple button on the screen. You click on it and it does nothing. So hopefully at the end you should be able to see this is unlocked actually. I should like try and make sure it doesn't get locked. Oh, wow, it's still doing all these things. Okay.
And we're gonna add more.
Yeah, that's true actually.
Hey, at least I'm sure we're gonna take like caching into consideration.
Yes, we will.
Yes.
Yeah. So yeah, so you can see there's nothing in the app except for the fact that there's a button that says hello Asm, and just like stop with the notifications, man. I don't care. Go away.
You sure you don't want to take a survey right now?
Yeah.
It's one question, man.
So like all it does is this.
Why do you like the project view instead of the Android? Come on, give me a break.
Dude, the Android view, I don't even know who
Why
this
is there?
why
Why
it's
is there? Why is
Yeah.
there? But
I
because
don't
There
really
are-
want.
I was surprised to learn there are people that actually prefer it.
yeah,
Sure.
because of the bell curve, I'm pretty sure, right? But that's the fact that they can use it. It doesn't make it right. You know, that's the thing.
Okay, so now we have this ASM code. Okay, the button does nothing. Like I'm clicking on it, it does nothing yet. So don't worry about it. So yeah, the main activity is something very simple. So now I have this is the app. Notice I have a build source too, and I sort of like created some infra because had you seen me painstakingly write a Gradle plugin from scratch, that would have taken way too long. So I did some work previously to the video, so I came prepared. Don't fret though; it's like pretty straightforward. Yeah, this actually we don't need. Clearly, I was trying many things, and so here I just have a build source where I'm defining where to look for repositories for dependencies and for other plugins. So in case my plugin is using a different plugin, then it knows where to find it, right? And then the build Gradle KTS basically is the guts of the actual plugin. So here I'm saying I'm writing a Java Gradle plugin. I'm using the Kotlin JVM library. I'm using the Kotlin JVM plugin to write my plugin. And I set my toolchain to Java 17, and I have a bunch of dependencies. I notice I have a dependency on the Gradle API, the Android Gradle plugin API, and I'm using the Gradle Kotlin DSL because I don't want to write Groovy, clearly. And I'm depending on ASM core, ASM util, and I have test implementation on ASM test and Kotlin test. Very simple.
I just had a flash of what if we try and look at the bytecode of a Groovy class, and I'm like, no.
So it's
Why?
funny you bring that. I was talking to Aramus about like my experiments with ASM, and he's like, you know what we should do? We should write a profiler using your ASM tool to instrument Groovy and to instrument Gradle to see where Gradle's slow. And I'm like, yeah, good luck with that. Like I think that's something you might be interested in, but I'm like, I'm not sure I'm interested in.
So, I have other stuff to do.
Yeah. So, and here I'm creating a plugin called experimental tracing because I couldn't come up with a better name. The ID of the plugin is what is important. This is the ID that is used when you apply the plugin on the Android project that wants to use this plugin. Mm-hmm. And here I'm saying the implementation comes from this class called tracing plugin, right? That's the implementation class. Yeah. Now, of course, Gradle, it wouldn't be enough if you just did the right thing once. You had to do it twice. So for some reason, despite doing all this, I also have to create the following entry into basically I have to use the id.gradle.properties in my manifest inf/Gradle plugins, and I have to define the same information again in this manifest file. So Gradle.
It shouldn't be needed.
I don't know. I tried it without it and it didn't work. So I'm like, I added it back. I don't know. I'm not.
I need to do how that works in Joule because I managed to get it to work in an easy way.
Yeah. So this is the plugin. This is the guts of the plugin. And you might be wondering how I came up with like the right architecture. And the way I did this was I looked at Android Gradle recipes. So Android Gradle recipes is a fantastic GitHub repo maintained by the AndroidStudio, Android Gradle team. And so if you go to, if you Google, this time I'll actually Google for it.
Yes. Pay my salary, Rahul.
Right?
Oh, man.
So if you go to Android Gradle recipes, it's a fantastic project that basically shows you how to do all the things that you ever wanted to do, how to extend Gradle. And all I did was I basically saw extending AGP as an example, and I basically copied the guts of the repository setup to basically get started with the plugin. And this is what you want to do also. So you never want to write this by reading Stack Overflow because like all the information that you read is probably wrong and it's probably super badad. And so like Gradle recipes
is also up to date as of last week.
This is also up to date. That's the important, right? That's the important bit. And so the tracing plugin does something very simple. It basically has clearly you could tell that I wanted to make sure that the plugin was actually being loaded. So let me get rid of that. So yeah, here I'm creating a Gradle extension called tracing plugin extension. And this is basically a way for me to sort of opt in classes that I want to instrument. So clearly I don't want to instrument the world, right? Like it's just too expensive and it's too noisy if I want to instrument like all the classes that I like have no control on. So I only want to instrument the classes, and I have this class called rule that defines how it goes about it. And so the rule is essentially has a function, it's an interface that has two methods. Basically, it exposes a function that says, given the class name, am I allowed to instrument this or not? Basically has an allows. And as owner, something that just transforms the name of the class to the JVM type owner, the type specification. So it has the L prefix and everything else. So yeah, the owner is literally you're replacing the dot with the slash to conform to the bytecode specification, right? So I just implemented that. So here I have a package rule, and if I basically want to make sure that I only instrument classes that belong to a certain package, then I want to use the package rule. And if I want to instrument a class of a well-known type, then I just want to say that I instrument the class rules, and then I'm doing the exact same thing. So I have these two rules that are defined, and I just have some helpers. So I have a package rule and a class rule, which is a helper that the callers of the plugin can use. And then I have to define this class called tracing parameters. And you might be wondering what this is. Don't worry about this yet. We'll come to this part. So here, the plugin extension is the is the DSL that the plugin exposes to the users of the plugin. So if you're wondering what that looks like, so if you looked at the example in the app module, if you look at our build Gradle KTS, notice I'm using this plugin, which is, remember the ID that we defined, com Rahul plugins tracing, which is the Gradle plugin. That's the ID that we used. And then here, the tracing is this is the extension. This is the tracing plugin extension that we defined in the plugin that exposes the DSL. So here I'm saying only instrument classes that are in this package, AndroidAsm, which is basically our entry point package. So if you look at com Rahul Android.asm, that's the entry point, and you're only saying just instrument those classes. Don't worry about instrumenting other things. So far, so good.
Yeah. By the way, I was just looking at the Jewel repo, how the plugins work. So essentially, I think there is no registration, nothing. You just create a file .gradle.kts and dump your stuff in there, and Gradle picks it up and registers as a plugin.
Okay, maybe I should try and remove it and see what happens again. Okay, and then in our tracing, I have the same traced. I have this annotation, but I haven't like actually defined the class that does the tracing, right? So let's actually copy over that. Shoot, I should have done that before. Hold on, let me go back and open Ultimate again so I can copy that class. So in our ASM playground, remember we had a class called tracing, which we were trying to use. Tracing, yeah. So this is the interface, right? Just copy this, and then just go away. Copy it here, right? This was the tracing interface that we wanted to use. And here, the implementation will actually do something real, right? So it'll basically use, so let's actually change a build Gradle KTS. Let's actually define, go to TOML, go to our TOML, park. 1 second, my keyboard is like freaking out right now. Right.
Is that one of those keyboards with a custom firmware? Yes,
that it is. All right, so that's actually define a dependency on AndroidX tracing because we just want to use Perfetto under the hood. So let's actually go to maven.google.com, and then let's see what version of tracing we have. AndroidX tracing, KTX. Let's see, sure, 1.2, Alpha 2, well, whatever, sure.
Yay.
Let's actually copy. Well, actually copy this. Go back to our, go back here, and then just like, it's just for define AndroidX.
I so wish there was an entry for the TOML syntax.
I know, that would be so nice. AndroidX tracing.
Who's the right person to annoy for this?
That is a good question. I don't know. So let's actually dump the text into even though we don't have that. So let's just use. So that's the group name, right?
Yep.
So you have the group equal to that. Shoot. And then you have the name equal to tracing KTX, and then you have the version.ref equal to tracing, and then we'll define that as 1.3.0 alpha 2. So we'll do tracing equal to that. Wow, that's not what I want to copy, but sure. Okay, then let's just get rid of that. So we've defined an entry point for tracing, and then we'll sync now. Right. Let's go back to our build create.ts and let's add a dependency implementation on libs.androidx tracing. Wow. Okay, so that got picked up. So let's sync again, make sure we have that implementation. Okay. All right, so far so good. Let's go back to our. Okay, let's actually do something like so. Let's actually create a new file for tracing, so it's clearer what we're doing. Tracing is the class that actually. We'll just copy it from here to here, just so it's in its own class and I don't overload what's happening here. Yeah, so here's this is the same class that we want to define an implementation for. So what I'll do is I'll basically say return object of type tracing. Of course, this already. And then I'll define methods, implement members, right? So I'll basically say val is enabled equal to AndroidX tracing.trace is enabled, right? If it's enabled, if it's not enabled, then we don't really care. So if
so it doesn't. I guess it's just if it's not enabled, then return.
Yes, basically. Actually, that's probably a better way to write it. If can you see how much I'm struggling with my new keyboard?
I remember you being good at keyboards.
There's so much muscle memory that you need to rewrite.
I know the pain of changing keyboards.
Keyboard are the.
I work on a Mac all day, and then when we do streams, I switch to Windows and I press all the wrong keys, even on the same keyboard. So it's I Alt C to copy because that's mapped to Command C on the Mac, but I'm on Windows, so it just yells at me. It's like no.
Yeah, sure. Just like suppress my. Yeah, it's complaining that I'm not surrounding it with an end section, but I know what I'm doing, so that's okay.
It's like, shut up.
Let's do end section.
Just suppress the whole thing and call it a day.
Interestingly, the end section doesn't need the name, so I'll just like ignore it because
keeping a stack by itself.
Yeah, it knows exactly. So let's see. Actions. Can I just ignore? Can I just like suppress this?
Yeah, the second one.
So nice. Thank God. I hate squigglies. Okay.
I so understand you.
So what we did is we wrote a very trivial.
I found it funny that end section doesn't have a lint check. Only begin section does. So you can still fuck up the trace, but lint won't tell you. Thor.
Yes. So here. I call begin and end section respectively on the implementation. That's exactly what I'm doing. And then I have this like marker interface called trace that tells if a class has been annotated, like has been rewritten. So it's just my way of like knowing if like assume like I'm just trying to be nicer to my users basically by not redecorating a class that's already been decorated if they built it with my plugin in their bytecode already. If that makes sense. Right, so if the marker were to exist, that means the class has already been decorated by the tracing plugin. So I basically don't touch that class. So that's what the marker is for. And so I wrote an implementation of tracing. And now we'll just do the exact same bit. So we have com Rahul Rav asm tracing. So now we'll just like write some code that shows what you want to do. So we can do that with this class. So we'll just call it test program like we did before, and then we'll just like simulate a bunch of methods. We'll just simulate 1 or 2 methods so we can sort of write the ASM that we want to write, right? So I'll just do that. Main. Let's say it calls method 1, and then let's define a function called method 1 that has println. Oh shoot. And then now we basically call tracing, but we want to write our tracing dot get instance dot begin section. The fun, and then tracing dot get instance or end section. Right. So this is the code that we want to write when main calls method 1. Of course, I need brackets here. So let's build this guy. Right. And once this test program is built, we can then use the ASM that got generated to sort of like see exactly what ASM we need to generate from the Gradle plugin. Does that make sense?
Mm-hmm.
Let's wait for a build. Okay. 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 So now we should be able to find our in the build folder. We should find our classes in the classes, and then if you go to debug ders com, you should see tracing. Shoot. Oh, actually, I should put the the sample outside maybe. Classes. Okay. Class debug. That's the test. Okay. Let's actually move the. I'll explain why I had to do this so you know what's going on. I basically ignored everything that's inside the traced because I don't want to instrument the code that is doing the instrumentation. So I'll just move the test program outside, refactor, and then we can rebuild. So we can see the class in the build out folder. Is it doing something? It is building something. Did it not build? Okay. Okay. Now we should be able to see the class file generated. No. TMP class debug. Okay. What? Where's our test program? Why is it not being generated? Did we just move it? Oh, there it is. Just took a while to show up. Okay, so now let's just copy it here and then look at the ASM view, right? So we know what's going on. So let's do that, and then let me open the editor now. Window, just drag it here.
I think you might have closed. Yeah.
Now I have to change the font size again.
Does it not remember? No, it does remember.
Yes, remember. So now we have the code, and so if you notice, test program main is calling main somewhere. Yeah, this is the part that is interesting, right? So we are here. We need to get the companion field from our tracing companion, and then invoke virtual before with the begin section on method 1, and then we'll do the end appropriately. So now if you go here, okay, let's go back, close, and then let's close these things. And now if you actually go to the Gradle plugin side, let's actually close all this too. In the build source, I have my visitor, just like I had my visitor previously, right? So this is doing the exact same thing. It's defining the tracing method visitor, which does nothing yet. This is the part that we need to implement. So we need to start like writing some bytecode. So we'll just like have the old bytecode as a reference. So let me just open up that code and we can just like tweak it so we can emit the right code with the new package name, because remember the package names have changed.
Yeah.
And when you're emitting bytecode, you want to make sure that the package names line up with the package names that you care about. And so what I'll do is I'll just like keep the old code as a reference, and I'll just like quickly do the class visitor.
Do the copy paste.
Yeah, do the copy paste. Yeah. So now what I'll do is I'll just do the exact same thing that we did before. So like if we are doing the same thing that we did before, so if it's a framework API that we don't care about, we just don't do anything, right? We'll just skip and then do the same thing before. So that now that we have that, and so now we'll just change the things that we need. So we need to call the static method companion to get the instance of companion, and to be able to call get instance, right?
Yeah.
So let's just do that. So where's so yeah, let's just do that. So just copy this bit, these 2 lines, and paste it here, right? And then if it's because you're just calling super instead of method visitor, you're called super.visitField, because I wanted to show you how you would write this code, and then you would just import these. Right. So now you define. There's some. You want us to remove the semicolons because you don't care. So now we have the tracing companion, and you're getting an instance. The instance is on top of the stack, right? And now we want to do the other bit, which is the load instruction with the trace section name, because we want the name of the trace section, right? And we call it section name here. So now we need to load the constant before we can call begin section, and we'll just do that now. Go back to our thing, and we'll just call begin section here. Oops. What did I do? I think I tried to build something before it was ready.
You command B instead of command V?
Yep, that's what I did.
Classic.
And then I'll just do super, and then I'll just do invoke interface. Right.
Okay.
So it's going to say save and move on. Okay. And then, yeah, so now I basically called begin section with the right trace section name, right? And now I can just now call the actual method, which is this bit. So I'll just do that. This is the actual method call that we are now rewriting, right now, and then we'll do.
And then you need to do the same thing as before,
same
but just
thing
call
as before,
and
with a small
instead
tweak,
of begin.
and then we'll call end section.
Okay.
Right. Basically, now we're done. So, and else we'll just do just say else we'll just do this. So we'll just like delegate to the inner, delegate to the decoration, and then now we're good. So now we finished the implementation of the visitor. We just remove all these notifications. So now that this is done, our class visitor is done. It's instrumenting the right methods, and then now we can get rid of our tracing. So now we can now clean up our code base, so we can just get rid of the test program that we defined to see what the bytecode looked like, right? So now we can just like delete this. Wow. Save, delete, done. All right. Now we have that, and now let's actually see everything work. So now if I build, oh, I haven't shown you. What is it talking about? Ooh, I actually imported the wrong. Clearly, I imported the wrong. So it's actually using clearly I'm using JDK as internal implementation for ASM. That's not what you want to do. So just like let's just get rid of these import and like re-import them correctly.
You just need to remove JDK.internal, I guess.
Yeah, so I need to import, but I want to import the right one. So it's not JDK internal, but it's actually org ASM opcode. We want it from ASM 9.7, which is my dependency. So I'll just do that, import, and then I'll just do where's there's some okay. This time IntelliJ knows that that's what I want to do, and then it basically picked up opcodes. Okay, so yeah, when you're copy pasting, be careful. All right, let's build everything now. So we have the method visitor working. I'll show you the remaining bits of the Gradle infra so you know exactly what's going on, and then everything will start to make a lot more sense. How are we doing for time, by the way? Like, I don't know how much time we have.
We should be wrapping up.
Okay, I'll try and wrap up quickly. All right.
So now when we build, we expect to have the decorated bytecode, right? Ooh.
What? What did I do?
Example instrumented test.
I don't know what it's trying to do actually. Like,
can you just remove Android test, the entire source set? Because I think it's trying to do something there that we don't care about.
Oh, I see. Yeah, let's just delete it. What happened here? Failure. Uh-oh. This is bad. Oh, I think I know what's going on. Okay, let me actually tweak that.
Well, the good news is it's running
it's running the actual method visitor. Framework API, super.visit, and that. It should be fine actually. Oh, did something wrong? Okay, visit method. Oh, did I not call end section? I called it end section. Okay, that looks right. Unless I missed something. Never mind. Let's see. I can actually tweak this a little bit more to see what's going on, but let's actually try this again. I think theme.kt is doing something wacky. Actually, let's try and rebuild this, but with
I don't know if it's because you're running build instead of running assemble debug or whatever.
So let's see what the actual error message is. It wouldn't be a stream if we didn't have an error message.
I mean, we already found the bug in a IntelliJ plugin, so par for the course.
Cannot locate. Oh, I spelled assemble debug. Is that wrong? Oh shoot! Are you kidding me?
It's because it's an app and you run it on the root probably.
Oh yeah, you're right. What are you talking about? Should I just? Maybe I should just assemble.
Okay.
YOLO.
Sure.
Okay, that works.
Are you in the right folder is the question now.
Ooh, that is a good question.
Because that you should have assemble debug.
Actually, I am in the wrong folder because I.
Okay, we changed the project, right?
Yeah, we changed the project. Android. We need to be in Android as in playground.
Aha.
Better.
This time it's doing something.
Yeah.
At least it'll tell us what went wrong.
It's not yelling at us.
Thank you, Sebastian.
You're welcome. I've been there. I've done
Negative
that.
array size. Perfect.
Negative array exception. Wow, that is rather strange.
Negative array size exception. So you try to create an array of size -6.
That is rather strange. What did I do here?
Do you need to do the recomputation that did we forget to enable those flags?
Yeah, that's what I'm checking. Hold on. I should have. Okay, let's see. Okay, let's look at our method visitor one more time quickly to make sure we got everything right. So we did the method one. We called method one, then we called method instruction, invoke instruction, and then that was it, right? Then we didn't have to do anything else. Okay, so that's fine. We called end section. Let me just make sure I actually copy it correctly, just in case I did that. Okay, that's fine. Android Asm interaction. Okay, let's actually just look at the generated code to see if there's something weird going on. If you look at intermediates, if you look at generated, if you look at temp, debug, theme.kt, we'll see the problem, I think. UI, and then let's actually open the Byte Code Viewer. Let's see what's going on. Let's see. Did it even try doing something here?
It doesn't look like it.
Oh yeah, well, this is the compose KT itself. Theme KT dot update code. Okay. Let's actually do something here. Let's just see what we did. The build source, method visitor. This looks right. What else can I check? But one thing I can do is I can see. Look at the stack trace again to see exactly what happened. So it's basically complaining that frame merge, compute all frames, negative array size merge, visit maxes, read code, class reader accept. So what does it complete?
So yeah, it looks like it's not regenerating the maxes, maybe.
Potentially.
Because it was visiting the maxes, right?
Yes, so no isolation class factory, it's calling the right things. So it's doing frame.merge. Let's see. This is so strange. I've never seen this happen. I swear I had this working in the morning.
Of course.
I mean, I can't believe you more than I mean, you don't understand how much I believe you, because this is perfect. This is how it works. This is our life.
There's one thing I can do to kind of be okay. I can just like basically say in my class visitor, I can just ignore. Oh, maybe I'm just doing something here. That's fine. Method. Okay, let's see if I need to do something here. Rahul, asm tracing. Let's actually ignore things in the UI package just to see if it just to see if we can work around this and we can isolate the problem to like a specific code path. Because I think something in the UI package, like the shape of the bytecode, is throwing things off, and I want to see exactly what. Main Java UI, right? So this is UI theme color. So let me just like not touch. So it's asm.ui.theme. I'm just basically treating that as framework code too, so I can sort of like.
You need to do slash instead of dot.
Thank you. So let me do that, and then I'll just say anything that's under that is something that I don't want to touch. Let's try and build this again. Making progress.
Not yelling yet. It's compiling.
No, something's still wrong.
Blom.
Error instrumenting class theme.kt. Why is it even trying to do theme.kt? That's the maybe our like filtering mechanism doesn't work very well. So let's see. Let's actually debug stuff here now. Let's actually add a debugger and see what's going on. And see if I think the owner doesn't look like what I think it looks. I think the owner doesn't have slashes; it has dots, because I always get them mixed up. So let's see if that is the case. Let's actually stop all Gradle plugin. Let's actually stop, and then let's actually see if I can run debugger. Oh, not that one. Debug. See, that's the one I want. So I want to run with debugging turned on, as not as a daemon, and then I want to turn on remote debugging here. Let's see. Then I can step into the code. Okay. See, the owner was Android Compose UI graphics, color KT, which looks right. So let's actually step to the next one. Next one. Android X Compose UI, Kotlin JVM Recomposer. Okay, so this is what it looks like. So this is the owner, com Rahul Rav.
And if you go step over that, does that flag get
so its
set
framework
properly?
API is true. Theme.kt is framework API is true, which makes sense because it is something that we're ignoring.
Mm-hmm.
It should just delegate to the super, which makes sense.
Is there any code after the if else?
Let me check. If else, there's nothing here. Oh yes, there is. This is wrong because we already. This is just leftover from the scaffold. I should check this. Okay, stop all. Let's try this again.
Let's see if it works now.
Okay. Let's just do example debug.
That would explain why there was like a negative array.
Yep. Because we were generating bytecode that literally made no sense. Because there's nothing on the stack to call that method.
But it was still trying to pop stuff.
Yep. It's good that ASM validates your bytecode and like basically like through
yeah,
yells at you for.
Don't you try crashing the JVM.
Okay, this time we managed to build.
Yay!
Clearly, I was an idiot. But good news is that we can now remove our hack and get rid of this bot, which we don't no longer need because it's actually worth instrumenting our themes as well. Why not? All right, let's build this now. We have everything we need. And when I build this time, and I go into build folder, and if I look at the temp, debug, com, application main activity, let's actually open it in the Byte Code Viewer so you know what it looks like. And then let's look at the decompile view. So if you notice,
I don't think it has built it yet.
Maybe it hasn't built it yet. Ooh, maybe I have. There's one last step remaining. Okay, it's still building. Okay. Let's see now. Oh, actually, I'm looking at the wrong place. I should look at intermediates. I think I should look at classes, debug, transform debug classes with ASM because notice we are transforming the actual. And then if you look at this,
that's the output of your task, right?
Yes, and then if you open this in the Byte Code Viewer, you should be able to see the decompiled view and notice begin section and end section wrapping.
Yes, it's there.
So it's there. So all of a sudden you are seeing every single class and method, every single dispatch getting emitted. And now Now the good stuff, if everything works well, and we turn on tracing,
it does.
which hopefully does, and we turn on tracing, we get a trace at the end that somewhat looks reasonable, right? Let's see now. Let's see what we get.
Because we didn't actually implement the tracing creation, the trace creation, it should work.
Yeah, for the most part. Okay, CD workspace, tools bin. So I have this tool called record Android trace, and I have I'm just going to start a Perfetto trace session that I'm going to record, right?
Mm-hmm.
I'm just going to start it, and I'm just going to launch our so I'm just going to call install release.
Does it need the profilable flag?
It has all that already, so
Okay.
I did all that.
Okay.
I should stop this and like restart it when I'm ready. So we have a really large trace, which we are not interested in seeing yet. That's okay. Okay. So now we're as we're installing the app, we're transforming the bytecode like we did before, right? Like remember, so that's the whole point. Okay. And then now let's launch our tracing session. So when we run the app this time, okay, now we're recording it, and then we'll go back to our device in Studio, and then just like play with the app a little bit. So let's go back to running apps, and then we'll just do that. I have to unlock it, of course. I don't know why it keeps getting locked. And when I launch the app, there should be playground, and I just launch the activity. Wow, what's it even doing? It's doing a lot.
Thinking very hard about life.
Ouch.
Oh, it can't find the application. Okay. Okay, I'll fix that. Okay. This is a stupid bug on my side, probably. Okay, let's see. Let's look at my build. Let's see.
New manifest.
Android manifest. See what my application is called. It's called, should be called application. I probably need non-create, and I should just delegate to super non-create, which is probably why it's like freaking out. And then my application looks right? Like this.
Looks okay.
Mm-hmm.
Okay. Okay, let's install release again. Let's go back and launch the app again. Okay. Whoa, running devices. Come on, don't get locked. You should like. What in the world? It's so strange. Oh, of course. What did it do? Oh no. I have to click. Look, let me use my phone directly. It's super hard to actually. There we go. App info, uninstall. Let's see what's going on. This time, like run lock. Oh, this. Why are there two? Okay, there's only one. Let's actually do this.
From Studio.
Do this. Yeah. See what happens. I should see. It's missing something clearly. Make application class not found as an application. What in the world? How is this even possible? What am I even doing? Package. Huh. That's so strange. This is the stupidest bug yet. I'm sure I'm doing something wrong. Rahul Rav, Android ASM, default first name. It's not even. It's unable to even find my application class. I
It
wonder
doesn't
why.
look registered in the manifest. There is no icon next to it.
Oh, interesting. Why would it not have that? Because I am specifying it, right? Do
Yeah,
I need
if you
to do anything?
command click it, it works, right?
Yeah, it works.
I don't know. Maybe the icon is not supposed to be there anymore. You can take it out. You don't need the custom application, right?
I don't need it, technically speaking.
Not for what we're doing.
Okay, stop it already. Okay, that's better. At least it failed. Oh yeah, it can't find the initialization provider. That's also right because I removed that from my manifest. Okay, that's fine. Let's actually bring it back because I was trying to do custom initialization and I didn't want that to pollute. That's fine. What in the world is going on? There's something super strange. It can't find Android.startup.initialization provider. I think it's just picking up the wrong manifest somehow.
Is that because you have a bunch of dependencies you probably don't need, like work managers trying to do whatever? I don't know.
No, that's fine. Yeah, I can get rid of that. But I think it's just picking up the wrong manifest for sure. 1 second. There's something. Am I doing the right thing? So it's in main, right? Like it's not like throwing it up. So it is the right thing. I mean, I can just remove AndroidX.work from our implementation just so we don't need that, and we rebuild. But that is so strange. Yeah, that's fine. That makes sense because we no longer have any of that. Where is this application KT coming even? I thought we okay. Let's get rid of that. Save delete. All right, let's delete that. Move on. Something's still wrong. It still can't find initialization provider because I'm sure someone else is using it. But I wonder what is going on here. There's something seriously strange. Okay. Let's see.
I think the app is cursed or something.
Let's see if I can just like unplug my thing and then just spin up an emulator to see if there's anything else strange going on.
I mean, it should run on the emulator, right? You'd think.
Yeah, but I think it crashed right away. I think it's the same problem.
Oh god.
Because I think it's not able to find bad call made by UID. Specified package is under UID -1, but it's not. I don't even know what that means. Like that runtime exception initialization provider. I wonder if we are doing something stupid here. Default application ID is that, and that matches the namespace. And am I doing something wrong? Am I doing something very stupid?
Do you have any like user ID defined in the manifest or anything? I don't think so.
No, hold on. Let me just try something very quick. Command / let me just like comment out the actual ASM. Let me just to see if it's throwing something off.
Just in case.
Yeah, it's possible that might be doing something. I think I'm building release. Maybe I should try debug and see what happens. Because I think things might be, well, they shouldn't get minified. Strange. Okay, so that worked clearly. Okay, that bit works. So let's just bring our things back. Oh, okay. Let me do one more thing. Class visitor. We just like stop doing the marker bit. Just maybe that's throwing things off. I just stopped adding the marker interface just to see if that makes it, because we're not using it anyway.
The traced interface.
Yeah. Wow, something very strange is going on. It's able to open code cache overlay. Okay, what's that even doing? Okay, let's just uninstall.
There is something really weird going on. Can you do a Gradle clean? Just, because you never know.
Yeah, it can't find AndroidX startup initialization provider. Let's actually treat that as a framework class, maybe. Like, I don't know what's going on here. Yeah, this is why you should try out live demos before you give a demo.
I mean, we can always try again after summer.
Yeah, we can. Let's see. I'll give it like a few more tries, and if it doesn't work, it doesn't work.
I would say we should give it maybe 1 minute, and then if it doesn't work, we should wrap up.
Yeah, because otherwise we mess up the schedule.
Yeah.
Right. Yeah, I think for some reason there's like something strange going on. I'm pretty sure there is something.
There will be something silly somewhere that.
Ooh, there's an error.
Invalid type descriptor.
Invalid type descriptors. Like I think we're failing to verify some class, which is interesting.
So the bytecode is wrong?
Clearly the type descriptor that we have is weird because it has double.
Oh yeah, it's okay.
I think we are just emitting bad bytecode somewhere. Like, hold on, if I can see if I can find something quick.
This look legit.
Get static class.name. So that.
Oh wait,
that looks...
is the companion is the fully qualified name probably?
Which one?
Where you use companion in the strings.
Oh my god! Like freaking backslashes, man. I kid you not. Is that
that looked like a fully qualified name, yeah. So
kids, don't copy paste code. Seriously, if this is it, like I'm going to be very, very upset.
It probably is.
Well,
hell?
I think it's perfect. Ending cursing, ending the episode cursing.
Oh my god, this is so upsetting. We did all the hard parts and we got string interpolation wrong. Can you believe it?
Yes, that happens to me every other day.
Okay. Let's see. Did it do anything?
Scroll.
To the bottom.
Yeah, no, scroll to the bottom because there is so much in the error log.
No, in the log. You were like
In the log.
in
No,
very,
I'm just
very
making sure
old log.
I have everything correctly done. Okay. Let's see. In the error log, right? Sorry. I think it's doing the same thing. It's trying to overlay. I think I just need to notice how it has many classes.
Yeah.
I'm just going to try like completely building from uninstalling and reinstalling. So let's just try that, and if that doesn't work, we'll just like wrap up. AndroidStudio does something clever. Tries to do something clever to speed up uninstallation, to do the debugging more nicely. But let's actually build clean rebuild project. Or I should just like actually clean and rebuild.
Should be the same thing.
I don't want to take a chance. Well, okay.
So in the meantime, I will put in the log in the
Ciao,
chat.
Sebastian.
Yeah, I know. I'll put in the chat the link to the to a 25% discount on DroidCon London tickets.
Mm-hmm.
Okay. Let's go back to our thing and see if this works.
So if you folks want to go to DroidCon London and save a bit of money, there's I think the first 10 people. Doesn't
works.
explode anymore.
Does it explode? Okay.
Yay.
So now this time, let's actually run the app with the method trace because we haven't turned on tracing yet. How do you go back? Why can't I swipe up?
Because it's a 3-button nav, so.
Oh God, why?
Yeah.
Okay.
Because
let's
AOSP.
actually see. Let me just force stop. So it's not running. Let's go back to our thing. Let's spin up. Let's do record Android trace. Now we're running the method trace. We're running Perfetto. Let's actually launch Playground and then click the button a few times. Let's launch Playground again, just so we have enough information, and then just stop here. See what happens.
If we see the colors, it's fine.
All right, please. See, top app is awesome. Android app startups. Let's mark it. Let's see, awesome. Ooh, look at that.
Woohoo!
Victory.
So now we should see method 1.
No, you won't see method 1, but you will actually see.
Oh, sorry. Yeah, no, we don't have those anymore. But
you'll actually see like this is all. Yeah, see, you notice how you can see every single. You can see that we started to, like you can see like every single. So you can see that we called the traversal called measure, called recompose, called the lambda, which called centered button. So every single time our methods got called, you can actually see method tracing endpoints, which is quite nice. So you can actually like try and figure out what actually happened. Like any single, you can actually add like a lot more context to the trace this way. And this is super nice. Like what I really wanted to show was like when you click a button and you like run a worker in Work Manager, then you can see those entry points a lot more defined, because right now you're just looking at like the activity, right? But you can actually still see all the typography and like all the invocations that you're seeing are like show up in the trace. So yeah, that was the demo. Sorry that took a while, but yeah,
we did it.
We did it. We did it.
So we have should we call this Rahul trace now?
Sure. You can call it you can call it whatever you want. But yeah, this is a this technique comes in handy a lot more than you think. You can actually like tweak the bytecode, and you can do a lot of like clever things. And
You can also
which,
shoot yourself in the foot in a
yes,
lot of
clearly,
interesting ways.
in a lot of interesting ways. Because I think I spent too much time doing the first part of the demos, I should have spent, being careful with the backslash thing. I hope they fix. I know they're fixing this in Kotlin too. I can't wait for this to like not be a thing. So yeah, if you have any questions, I'm happy to answer them later. I'm sure we're running out of time. So
yeah, we are like 35 minutes over time. So
yeah, so sorry. If you can just cut the parts that the demo didn't work, that'd be
yeah,
great.
this is gonna be like a neon cat going through the screen, and then we're
I know,
done.
it's like-
It works.
It works! Yeah!
Yay!
Yeah, and then we just skip all the drama.
Yeah. Rahul, thank you very much.
No worries.
We're looking forward to having you back next time for, who knows, maybe camera hacking, maybe, who knows.
Bluetooth hacking,
Yeah,
hacking.
why not? Why not? Folks, in case you missed it, I mentioned it earlier, but we're going to go on summer break from now until September. Exactly when in September is to be defined. It's probably second half of September, but I don't have dates yet. So yeah, we'll see you folks soon. Have a great summer. Take advantage of the links that I put in the chat for DroidCon London, because 25% off. Why not? And yeah, we're always going to be on our Telegram group anyway. We're still going to be answering if you're over there. And yeah, have a great summer, folks. Or winter if you're in the other hemisphere, I guess.
Thank you, Rahul. Ciao.
Thank you.
Bye-bye. That was a joke. We're here still next week. I'm sorry. I just messed up the calendars.
So
fake outro and now real outro. See you next week.